This is the third video in the pre-lab for Lab 3. Again, we had an offset of 3. Just want to explain once again that this axis, this is the slider axis, and the way this is O2. This in Norton's nomenclature, this is right. The ground link is link 1. This red link right here is link 2. O2 is its pivot on the ground. So the distance from this link to perpendicular distance from this ground pivot right here to the slider axis is 3, right? And the slider axis is rotated 90 degrees. So that's the way that works. And so anyways, you can run this, and if we go to print, whoops, sorry, next, and then print. And again, if we select something like, suppose we want the velocity of the slider. Again, there's a bug in this software. You can see there's the v sub x, v sub y, v magnitude. They can't all be the same. So what you do is just select the top one, the thetas first. And then now if you select the velocity of the slider, right, as expected, for this particular case, in the x direction, it's always 0. Right, so now these numbers are correct. And what you'll need to do is plot out, right, in the lab. The lab asks you to generate plots of position and velocity curves of point P, the coupler point, as well as the angular velocity of the coupler. So you can do that with this software. Let me just get back here. There we go. And this time we'll select plot. And now from the different preset functions, we can get the different curves. So if we want to plot, for instance, the velocity of the coupler point, x, y, magnitude, and angle coordinates. So there we go. That's the x, y, and magnitude, and this is the angle of the velocity. So you can see, for instance, right here, this is the y velocity. So when the y velocity is 0 and the x velocity is positive, it's going to be at an angle of 0 degrees, right? So we drop down here, you can see, yep, there's an angle of 0 degrees. In the same way, at 90 degrees, the x, right, at around, there's 90 degrees right there. Well, the vector is pointing straight up, right? So the x coordinate will be 0, and that's where the x coordinate is 0. So anyways, you can generate, you know, whatever plots you need in this way. So the next thing you'll do in this lab is pick an angle for the crank. And each member of your team, by the way, should pick a different angle. So because on the lab worksheet, you'll do copy and paste of screenshots of this mechanism, but in terms of the hand calculation, everybody wants to try a different angle. And then, of course, you can compare it to the value you got with Norton or Algodo. So here's what I'm talking about. You know, at this point, for this part, you'll pick a crank value. You can pick something that's, you know, convenient or fairly obvious to convenient to calculate. There are some angles that are going to be easier than others. And then you can use MathCAD if you like. I would personally use the MathCAD and use the method of instantaneous centers, and then you can get that part. So the next part of the lab, okay, is you'll build the mechanism and attach a VEX module and VEX encoder to it. Then just create some sketches of coupler curves. If it's difficult running this with the VEX motor, then you can just, you know, turn the crank by hand and sketch out the mechanism that way. Just make sure that you have a clear outline of the mechanism when you do this. And then you'll run the motor, and you can collect data at a 50 hertz rate. And I'm going to have to stop here and pick up with the next video.